connection. Determine line and phase voltage for the data connected system. Determine the line and phase current for data connected system. Drawing label the phasor diagrams for data connected system. State the limitations of the data connected systems and the connected data connected load. So this is a data connection. In this case, this connection you see that U1, U2. So U2 connected to V1, V2 connected to V1, W2 connected to U1, and then connected to supply. This is a data connection. So this is a voltage, so the three-phase data voltage. So the red, blue, and the black voltage. So in this case, this is the between U1 and U2, V1, V2, and the V1 to V2. So this data connection. So this data connections you can see the data diagram. So that data. So in this case, the phase and line voltage you can calculate it. So this is a VA says a line voltage. Similarly, the VB and the VC is a line voltage. So the V line is equal to the VAB. Also, this V line also equal to VBC and V line also equal to the VCA. So this data connection is a voltage and current relationship. So line voltage are the same as a phase voltage. V line equal to VB. And the line current IE is a line current IE is coming here. And also line current IB and line current IC. Then go to the IAB, IBC, and ICA. Those are the phase currents. So the line current is the difference between the two phase currents. So if you want to calculate the IA, the equation the IAB minus ICA. So this is the IA. Similarly, the IB. IAB can be calculated IB and sine theta. So the IAB is an angle 0 degree. IB is IN sine theta minus 120. So this is IBC IN minus angle minus 120 degree. ICA is IN sine theta minus 240. So ICA equal to IN angle minus 240 degree. Line currents are equal to the IA equal to IAB minus ICA. So this is the we see a better diagram. IAB is IN, ICA is IN. So that then IA is equal to IN minus IN 100 minus 120 degrees. So this is that you can calculate. So that can, this current is IA equal to root 3 IN angles are minus 30 degrees. Similarly, therefore the data connection free and currents are voltage and current relationship. Line voltage are equal to VA equal to the phase voltage. Line voltage equal to phase voltage. VA equal to VB. Line current equal to difference of the two phase currents. IA equal to I phase 1 minus I phase 2. So this is also equal to root 3 times I phase. So then we have to calculate that determine the current for a three-phase motor stator winding, which has an impedance of the 20 ohm per phase when it is connected to the 450 volt 50 hertz supply. So in this case, the three resistors, 20 ohms are connected between across A, B, B, C, and CA. So that the voltage is a 450 volt 50 cycle per second. VV equal to VI equal to 450 volt. Similarly, IP can be calculated. The VV divided by ZB. Then we also calculate 415 divided by 20. We got the 20 by 75 ampere. IA equal to root 3 times IB. So root 3 times 20 by 75 ampere. So then you got 35 by 94 ampere. This is the line current calculated. The next problem, determine the phase current for the three-phase data connected transformer, which deliver is a 40 ampere when it is connected to a 11 kV 50 hertz supply. So in this case, this connection is connected. So this is ABC data connection. So in this case, the voltage line voltage is 11 volt, 11 kV, 50 hertz. Line current are 40 ampere. Then we also calculate the IAB. So this is phase current. Line current IA divided by root 3. So the I phase is equal to 40 by root 3. You got the 23 by 1 ampere. Similarly, the next one is we have to determine the phase current for a three-phase data connected resistive load, which is a line current of 34.6 ampere. So in this case, we make the connection ABC, the data connection. So 34.6 ampere is the line current. The IAB is the phase current. IB equal to IA by root 3. So the 34.6 by root 3, you got the 90.98 ampere. The next one is determine the line current for a three-phase data connected resistive load, which has a phase current of 100 ampere. So this is the ABC. We made the connection here. So the 100 ampere connected go from the A to B. Line current IA is root 3 times I phase. So the 100 multiplied root 3, you got the 173.2 ampere. Determine the phase voltage and the current for a balanced three-phase data connected resistive load, which has a line current of 100 ampere and a phase impedance of the 20 ohm. So this is a 20 ohm phase impedance we connected. So the 100 ampere following into the IAD. So IB equal to I divided by root 3. So the 100 divided by root 3, you got the 57 by 74 ampere. V equal to V phase equal to I phase multiplied Z. So the 57 and 74 multiplied 20, you got the 1.154.84. The next one is the determine the line current for a three-phase motor, which has a balanced impedance of the 20 ohm phase when it is connected to three-phase 400 volt 50 hertz supply. So in this case, we calculated the line voltage are the 400 volts are 50 hertz. So the resistance are the 20 ohm connected. The phase current had to calculate that. So in this case, VB equal to V equal to 400 volt. I equal to VB by ZB. So 400 by 20, you got 20 ampere. I equal to root 3 by IB. So root 3 multiplied by 20, you got the 34 by 64 ampere. So this is the biggest one. Next one. Three-phase star data system. Star data system. So the sort of problem is low voltage AC circuit, star data system. And then in all of this lesson, students should be able to identify interconnected star data system, show the relationships between the line phase voltage and the current for a three-phase system, take the effect of the passing phase winding in the three-phase system, connect the star data system. So in this case, this is a star connection. The voltage and current relationship is a line current equal to the phase current. This is a star connection. So this is I equal to IB. And also the current and the neutral current is equal to the neutral current plus IA plus IB plus IC equal to 0. Line voltage is equal to difference of the two phase voltage. So this is equal to V equal to root 3 times PT. And the data connection, voltage and the current relationship. So line voltage is equal to the phase voltage. V equal to VB. Line current equal to difference of the two phase current. So I equal to root 3 times I phase. Where to calculate? Determine the line current of the three-phase data connected motor, which has an impedance of 24 ohm phase when it is connected to a 240 volt star connected transformer. So in this case, we connected a 240 volt star connection, and also data connection is a 24 ohms are connected to data. So in this case, the supply voltage VB 240 volt, V equal to root 3 times VB, so that root 3 times 240. So you got, and also the VA equal to 415 volt. And so that in this case, VA equal to 415 volt, VB equal to 240 volt. In this case, VA equal to VB for the data connection. So IB equal to VB by ZB, so you got 415 by 20 volt, you got the 7.32 ampere. So I equal to root 3 IB, so root 3 multiply 7.32, you got the 30 ampere. So this is the way we calculate it. The next problem. Determine the current of a three-phase star connected motor, which has an impedance of 24 ohm phase when it is connected to the 240 volt star connected transformer. So this is a star connection transformer, 240 volt, or the supply voltage 240 volt, and also the star connection 24 ohm. So ABC supply. So in this case, the supply is V equal to root 3 times VB. So in this case, VB equal to V divided by root 3. So the IB equal to VB by ZB. So 240 by 24, you got a 10 ampere. I equal to IB equal to I equal to 10 ampere. This is for the star connection. Data connection, I equal to 30 ampere. The next problem. Determine the current in the element of the three-phase data connected heater, which has an impedance of the 41.5 ohm per phase when it is connected to a 415 volt 3 watt supply if the fuse in the phase C has a blown. So in this case, this is the connection, data connection, 41.5 ohm. Data connection, supply voltage V equal to 415 volt. So the next ones are, in this case, are normal operation for all the data connection complete supply. In this case, IP equal to VB by ZB. So the 415 divided by 41.5, you got the I phase equal to 10 ampere. So then you can also calculate the line current. So line current root 3 like phase current. So the root 3 multiplied by 10, you got the 17.32 ampere. Then fuse blow. The fuse blow. So then this is the fuse blow is a IAIB here, IC equal to 0. Therefore, the current flow to here, in this case, are the IAIB. So what happens is that 41.5 to 45.5 ohms are connected in parallel. And that's also connected in series and parallel with the 41.5 ohms. So IB equal to VB by ZB. We calculate that. So the ZAB divided by VAB by ZAB. So the 41.5, 41.5 divided by 41.5, you got a 10 ampere. IAB. IAB1 is 10 ampere. IAB2 is going to be a VAB by ZAB2. So this way calculate 415 divided by 41.5 by 41.5. You got this IAB2 is a 5 ampere. Then I equal to IB equal to IAB1 plus IAB2. So that way the 10 plus 5, you got the 15 ampere. Determine the phase voltage and the current for the element of three-phase star connected theta, which has the impedance of the 24 ohm phase when it is connected to 405 volt 4 hour supply if the fuse in the phase here flow. So in this case, the three-phase are star connection. Supply voltage is line voltage of 415 volt, phase voltage is V by root 3, so that VB equal to 240 volt. In this case, that's star connection 24 ohm. So this is a normal operation. IB equal to VB by ZB. So 240 by 24, you got a 10 ampere. IA equal to IB. So that in this case, IA equal to 10 ampere. IM plus IBA plus IB plus IC equal to 0. So IA equal to 0 ampere. That's what we call it. Then the fuse in the C has below is IC equal to 0. So in this case, what happens is IC equal to 0. In this case, are the IN calculated IN equal to IL equal to 10 ampere. You got. So this is equal to 0 volt. Fuse blow operation, IB equal to the VB by ZB. So you got this is a VC equal to IC equal to 0. So the what happens is that IAB is a VAB is a 415 volt. So current flow to here and all current flow to the 24 and 24. So in this case, are the I equal to minus IB. Then you got 415 divided by 24 plus 24, you got the 8.65 ampere. Then you got a star voltage, V equal to VB equal to VC equal to V phase. So the VAB equal to root 3 times our VP, so you got calculated. And also the VB is equal to root 3 times VB, V is equal to root 3 times VP. So then, so VA equal to VB equal to VC equal to VP. So this is star voltage is a phase capacitor. So in this case, VAB equal to root 3 times VP. Then you got VAB equal to not equal to the root 3 times VP. So this is what a star voltage capacitor. This is delta voltage. VAB equal to VB equal to VAC equal to V phase. So in this case, VAB plus VBC plus VC equal to 0. And delta voltage phase capacitor, that we got. VAB equal to VBC plus VC are not equal to 0. VAB equal to VBC and VC equal to 2 times VAB. So this, if the rotation is correct, this is a rotation correct. Voltage reading is 0. Any phase reverse, voltage reading is a 2 V phase. So this is the way we got. The open delta connection. So this is supply and there's a load connection here. In this case, 3-phase input equal to 2 single-phase transformer and 3-phase output. So simple and easy to construct the phase and line voltage. In this case, I equal to ID. Does not have the same power capability. They only got this 57 by 7%. The last way, 3-phase energy and power.
Poor memory of no food in here. Jonya Genatin, Matapinari. Poor memory of no food in here. And you could do one of it all.
Okay, the next one. Energy and power in three-phase system. At the end of this lesson, students should be able to calculate the true apparent and rated power in a three-phase system, measure the true power in three-phase system. So in this case, we can draw the power triangle. So the horizontal is a real power P, Vi cos theta, and the vertical rated power Q, Vi sine theta. And this hypotenuse is the apparent power, S equal to Vi. Power factor lambda can be calculated P divided by S. So in this case, real power Vi cos theta, reactive power Vi sine theta, and apparent power S equal to Vi. The power factor lambda is calculated to real power to the apparent power. So in this case, our cos theta can be calculated P divided by S equal to lambda you got. And the unbalanced of three-phase system. Unbalanced three-phase system, this is a three-phase system, P1, P2, P3, the real power, Q1, Q2, Q3 are reactive power, S1, S2, S3 are the reactive apparent power. So in this case, angle theta 1, angle theta 2, and theta 3 are the power factor angle. So that we add all of them, so that we add the P1, P1, P2, P3, you add, all the Q1, Q2, Q3 you add. Then you can see the total line. So this is the dotted line is a total apparent power. So in this case, real power in the three-phase system can be calculated. Pg equal to Pa plus Pb plus Pc. Similarly, in a balanced three-phase system, this is a balance of all the power triangles are the same. In this case, we can calculate that P total is equal to P1, P2, P3, Q total is Q1, Q2, Q3. Real power three-phase system can be calculated P total equal to Pa plus Pb plus Pc. So the real power in any three-phase system, P total equal to Pa plus Pb plus Pc. In a balanced three-phase system, P total equal to 3 Pp. In this case, 3 multiplied Vp Ib cos theta. In a star connected system, Vp multiplied Ib. This is equal to Im multiplied Va by 3. Data connected system, Vp minus Ib equal to Vl multiplied Ia by 3. In this case, P total equal to 3 multiplied Va Ia by 3 in cos theta. So you got the root 3 Va Ia cos theta. So this is the way we calculate the total power total. So in this case, power total equal to root 3 times Vp Ib cos theta or root 3 VL IS cos theta. In this case, Vp is a phase voltage, Ib is a phase current, VL line voltage, and IL line current. Where to calculate? Determine the true power delivered through the three-phase data connected induction motor, which draws a balanced line current of 20 ampere at the lagging power factor of 0.866 from the 415 50 Hz supply. So the VA equal to 415 volt, IA equal to 20 ampere, lambda equal to 0.866. So PD equal to root 3 VA IA cos theta. Root 3 into 415 minus 20 minus 0.866. You got it. 12.449 watt. So 12.5 kilowatt. The next one is a determine the line current delivered by the 111 kV transformer to a three-phase balance load which uses 300 kilowatt at a lagging power factor of 0.9. So V equal to 11 kV, PT equal to 300 kilowatt, lambda equal to 0.9. So I equal to PT divided by 3 PL cos theta 300K divided by 3 into 11K into 0.9. So you got 75 ampere. The next one is to determine the true and the reactive power that can be delivered by a three-phase transformer rated as a 50 kVA if the load has a 0.5 lagging power factor. So in this case, I told the apparent powers are ST, the 50 kVA, lambda 0.5 lagging. So in this case, we draw the bar trigger S, P, and Q. So P equal S cos theta. So the 5 lambda. So you got a 50 K into 0.5, you got a 25 kilowatt. Q2 equal to square root of S square minus B square, so 50 square minus 25 square, 43.3 kVA. So in this case, theta equal to cos inverse lambda. So cos inverse 0.5, you got a 60 degree. Theta Q3 equal to SI theta, so 15 multiplied by 0.866, you got a 43.3 kVA. The next one, a three-phase balance loads requires 180 kilowatt of the power when operating at the 0.6 lagging power factor and connected to the 415 volt 50 Hz three-way supply. Determine the kVA rating and the capacitance of the star-connected capacitor band that will improve the power factor to 0.9 lagging. So in this case, firstly, we have to draw the construct the original power trigger. So we draw this power trigger, PD 100 kilowatt. Scales are 1 centimeter, 20 kilo. So in this case, 100 kilowatt we draw. And then also the particle line, we draw the use the rotator and the lambda 1 equal to the 0.86, so that you got the cos inverse of 0.6, you got 50.3, so you draw the slide. So this is the original power. So in this case, you measure the particle 1, so this is 240 kVA. So then lambda 2 is a 0.9. So in this case, cos inverse 0.9 is 25/84. So you minus 25/84 and you draw the line. And then you measure, so Q2 equal to 88 kVA. So this is the kVA rating. So that's the difference between the Q1 and Q2 is the red one. So Q is equal to found 240 minus 87, you got a 153 kVA. So the three-phase balance load. So in this case, we have to calculate capacitance of the capacitor band. So it is QC 154.53 kVA. So the QB equal to QC by root 3. Because of the three phase, right? Every phase. So this is the phase of rated power can be calculated QC by 3. It is 153 by 3. You got the 31 kVA. And then you have to calculate the HB. PB square divided by QB. So you got PB can be calculated P by root 3. So you got the 240 square divided by the 51000. You got the HB equal to 1 by 130. HB equal to 1 divided by 2 by FC. You substitute. C equal to 1 divided by 2 by FHB. So the 1 divided by 2 by into 15 1 by 13. You got the 2 by 82 millifarads. So this is the way we calculate it. So the power factor in the three phase system. In this case, 1 meter we both connected. So N and L1, V1, V2 here. This is the what? W2 and W3. So the P total is equal to PA plus PB plus PC. So the advantage is it can use this is for the 3 watt meter and 4 wire method. It can be used for on the balanced or unbalanced load. Total power easily monitor. So reasonable accurate. So disadvantage is the 3 watt meter required. It requires a neutral or scarce system. So in this case, only 1 watt meter methods move from phase to get the each reading. So in this case, 1 watt meter, you can move from phase to phase and you can read. So the P total is PA plus PB plus PC. And power measure in 3 phase system, so this is the 1 watt meter connected here. In this case, the only 1 meter required. Simple and cheap, can be used on a balanced or unbalanced load. Disadvantage is not very accurate in unbalanced load. So this is what we connected. So this is what artificial star point. The 3 watt meter method is we connected to artificial star point. Can be used for the balance or unbalanced load. To the power easy monitor, reasonable accurate. Disadvantages are require the 3 identical watt meter. Another thing is a 1 watt meter and a 3 phase wire method. So this is the connection. So this is for the connected to the artificial star point and you connected this watt meter. So the only 1 meter can be used simple and cheap. Can be used on the balance or unbalanced load. Disadvantage are the must be construct artificial star point. Not accurate on variant unbalanced load. Need to reconnect each phase for the unbalanced load. And there are 2 watt meter method. So we connect the 2 ammeter like this, P2 will be P1 plus P2. And advantage can be used on the balance or unbalanced load to the power easily monitor. Only 2 ammeter required. Disadvantage can be used with the 3-wire system only, not accurate for the load with the low power factor. And so this is a 2 ammeter procedure. So P2 is equal to P1 plus P2 for balance load. Locate the W2 in the phase immediately following W1 in the phase sequence. So theta equal to root 3 times W2 minus W1 divided by W2 plus W1. So this is 2 element 1 meter can be utilized. This is for the G102. Then we also go to the G101. Magnetic theory. 3-4. So this is we call the magnetic circuit. So the magnetic circuit. So objectives at the end of this session, students should be able to describe and draw the magnetic circuits, describe the relators Rm and the AFS in magnetic circuits, describe the relationship between magnetomotive force Fn plus phi and the relators Rm. Describe the permeability mu and the AFS on the magnetic circuits. Describe the factors that affect the flux density. Describe the turns of magnetizing force and calculate the value of the Fn, Hb, mu, Rm, and phi. So this is a magnetic circuit we connected. So this point your magnet and this is coil connected to the battery. And the electric circuit can be drawn. In this case, the current flow in here. So in this case, the indicators and not both. It can become a magnetomotive force. So MMH is a magnetomotive force. So this is similar to the EMF. So EMF is electromotive force. So this is a magnetic circuit. This is electric circuit. The magnetic force, the plus are the phi, the plus. The phi is the flowing. And similar to the electromotive force is a EMF. The current I flowing. So that this is the current plus of flowing here. So this is a magnetic circuit. And this is the electric circuit. So in this case, Rm equal to the reluctance. For the electric circuit, Rm to resistance. So reluctance can be calculated. So this is the material opposition to magnetic field. This is the reluctance. It's similar to a resistance and it affected by the same physical properties. So the Rm is a direct proportional to the length of the magnetic path. So Rm equal to inversely proportional to cross-sectional area of magnetic path. Ra is 1 divided by absolute permeability. So this is the relationship of the Rm. So Rm can be calculated as divided by mu A. In this case, are the Rmu magnetic reluctance. The unit is ampere turn per Weber. A is the length of the magnetic path. A is the cross-sectional area of magnetic path meter square. Mu is the absolute permeability. And this is we also calculate the permeability. So the definition is a material's ability to accept the magnetic field is called its permeability. Permeability is similar to the conductance. So permeability of a 3 AMU0 is can be calculated 4 by 10 power minus 7, you have 12.57 10 power minus 7. All other permeabilities are A flat as a value related to the permeability of the free air. The related permeability is mu R. So absolute permeability can be calculated as mu equal to mu0 into mu R. So this is when the good magnetic properties and has a high lattice of permeability. So we can calculate the mu equal to mu0 mu R. So 4 by 10 power minus 7. So 12 by 5 7 10 power minus 7. In this case, copper, related permeability mu R is 1, absolute permeability is 12 by 5 7 10 power minus 7. Aluminum, related permeability is 1, absolute permeability is 12 by 5 7 10 power minus 7. Iron, relative permeability is 9,000. Absolute permeability is 11.31 into 10 power minus 3. So iron, relative permeability mu I is 55000. Absolute permeability is 69.13 into 10 power minus 3. And also the new material is a relative permeability is equal to 100,000, but absolute permeability is 125.7 into 10 power minus 3. So in this case, the current circuit, you can see the length of the circuit is 250 millimeter, area is 175 millimeter square, mu is 10 by 6 into 10 power minus 4. RM can be calculated at divided by mu is. So this is for the 250 into 10 power minus 3 divided by 10 by 6 into 10 power minus 4 multiplied 175 into 10 power minus 6. You got the 1 by 337 into 10 power 6 ampere turn per Weber. We calculated. The current flow is here. So in this case for the Fn, so magnetic motive flow is Fn. So Fn equal to I multiplied N. Current multiplied number of turns can be calculated. So this is the flow is a part of the load reluctance. So that phi can be calculated as In divided by Rm. So Rm is reluctance can be calculated. So in this case, I is to 22 ampere. N is to number of times 1,500 times. Rm to 40,000 ampere turn per Weber. We have to calculate the magnetic motive force and a plus 5. So in this case, Fn is connected to the similar to the Rm. The plus 5 is chlorine. So magnetic motive force can be calculated. Fn into I multiplied M. So that 2 into 1,500, you got 3,000 ampere turns. Plus 5 can be calculated Im by Rm. So you got 3,000 divided by 4, 40,000, you got 75 milliweber. So the when the basic connection in this case are the I is 1.5 ampere and you go to the 800 turns, Rm can be calculated 50,000 ampere turn per Weber, where you calculate the magnetic motive force and the plus 5. So in this case, the current flowing, so the Fn equal to the magnetic motive force and Rm here plus 5 flowing. Then you got calculate the magnetic motive force Fn. Fn equal to I multiplied N. So that 1.5 to 800, you got the 1,200 ampere turns. Plus 5 can be calculated Im by Rm. So this is 1,200 by 50,000. You got the 24 milliweber. Now also that this is the magnetic relay. So kind of connection here. In this case, the plus 5 can be calculated 50 milliweber. Number of times is 1,000 times. Rm is 20,000 ampere turn per Weber. We have to find the current I. So that we calculated the phi equal to Im by Rm. So that I can be calculated phi Rm by M. So you got a 50 meter into 20,000 divided by 1,000. You got the current I 1 ampere. The next one is the plus phi, the 2.5 milliweber. I equal to 200 milliampere. Rm can be calculated 60,000 ampere turns per Weber. We have to find the amount of turns in the coil N. So in this case, phi equal to In divided by Rm. So the N equal to phi Rm by I. So you got the 2.5 into 60,000 divided by 200 meters. So you got the 750 times you got. What is the flood density? This is area. Area is width multiplied height. So in this case, the flood is in a Weber can be calculated. P is the flood density, so pi divided by area. So this is the flood density. And this also this is the circuit side. So it also phi b equal to pi by a. In this case, this area can be calculated pi d square by pi r square or the pi d by 2 so the whole square. So in this case, the SI unit of magnetic flux is a Weber. So 1 Weber equal to 10 power 8 magnetic lines on the pole. Magnetic flux by a unit area is a flux density B. The SI unit of flux density is Tesla. So the 1 Weber meter square equal to 1 Tesla. So in this case, V equal to 5 by 8. Flux density divided by V is the flux density, 5 the flux in Weber is the area meter square. So this one you also calculated 5 equal to 0.55 milliweber crossing the area 500 millimeter square. We have to calculate the flux density B. So in this case, we calculate the flux in floating plus in this case B equal to 5 by 8. So the 0.55 into 10 power minus 3 divided by 500 into 10 power minus 8. You got the 1 by 1 Tesla. Magnetizing force H can be calculated. This is the magnetic field strength divided by L. So in this case, Im by L. So L is the length of the magnetic path. The find the magnetizing force. N equal to 300 times, I equal to 4 ampere, L equal to 200 millimeter. So H equal to Im by L. So we can calculate 300 into 4 divided by 200 to 10 power minus 3. You got a 6,000 ampere turns per meter. We also need to find the magnetizing force. N equal to 1000 tons, I equal to 100 milliampere, N equal to 200 millimeter. So in this case, A equal to IM by L, so 1000 into 0.1 divided by 200 into 10 power minus 3. So you got that 500 ampere tons per meter. You calculate it. We also need to find the current. N equal to 1000 tons, A equal to 500 ampere tons per meter, A equal to 220 millimeter. So in this case, I equal to HL by N. So in this case, 500 into 20 into 10 power minus 3 divided by 1000, you got that I equal to 10 milliampere. We also have to find out the magnetizing force with this one. N equal to 1000 tons, A equal to 500 ampere tons per meter. So A equal to 200 millimeter, I 100 millimeter. We also use the magnetizing curve. The next one is magnetizing curve. So this is the magnetizing curve. So at the end of this session, students should be able to describe and draw the typical magnetizing curve, describe and draw the typical hysteresis curve, describe the meaning of the turn saturation, hysteresis, and losses in a magnetic circuit, compare the magnetic characteristics of number of materials, describe the magnetic losses, and their effect on the performance of electrical machines. What is the flux density? So this is the flux density here. Area meter square is, so this is the area. So this is flux density can be calculated 5 by A. And then, so this is what the flux density can be calculated. So the SI unit of flux density is Tesla, 1 Weber square by meter square is 1 Tesla. Magnetic flux density in the core of magnetic circuit dependent on the permeability, mu of the core and the magnetizing force. In this case, B can calculate mu into H. So in this case, B equal to flux density, mu equal to permeability, and the H is magnetizing force. Magnetizing current can be calculated. So this is the magnetizing force is here and the flux density. When the flux density, magnetizing force increase, flux density will also increase. So in this case, magnetizing force is a ampere turn per meter and flux density is a Tesla. So it is an A. In this case, this is A is our flux density cast iron and also cast T. So this is a magnetizing force for the A, cast iron, and cast T. And that is why the silicon C. Those are the magnetizing force, the relationship between the magnetizing force and the flux density for the cast T, silicon C, cast iron, and air. So the in this case, non-magnetic material is a magnetic force and the flux density are directly proportional. But the for the magnetic material, in this case, the depth motion will be the linear, but here is a depth curve will be happen. So this is more a reasonably linear operation relation in this region. This is why is a D point. And that's why with the saturation, because of the although that you are increasing the magnetizing force, flux density will no longer increase. So that's why the saturation. We have to calculate the magnetizing force H necessary to produce the flux density of 0.75 Tesla in 300 millimeter cast T, totalizing score with the coil with the 500 tons. So in this case, this is totalizing force with the score. So in this case, B equal to 0.75 Tesla and A equal to 300 millimeter. So in this case, N equal to 500 tons. So in this case, cast T. So in this case, they are cast T. Here is the silicon C, radium metal, and the cast iron. So in this case, we utilize this graph. In this case, we use the cast T. Cast T, we have to find this cast T equation. So for the magnetized BH path, so the B equal to 0.75 is Tesla. This one. In this case, you can find out A equal to 750 ampere tons per meter. So H equal to IN by L. So I equal to HL by N. So you got the 750.3 divided by 500. You got the 0.45 ampere. We also have to find the magnetizing force H necessary to produce the flux density of 0.75 Tesla in the 300 millimeter cast iron toroidal core for a coil with the 500 tons. So in this case, we use a cast iron. So we have to find a cast iron characteristic. So that for the cast iron, pH for the B 0.75 Tesla. So you find out the H. The H will be the 4,500 ampere gas per meter. H equal to IN by L. So in this case, HL by N is equal to I. So 4,500 multiplied by 3 by 500. You got the 2.7 ampere. So there's a pH curve. We draw the pH curve here. This is for the saturation point. And when the reduce, it will go like this. So there will be the residual magnetic dispersion. And here with the co-salted force. So this is for the calculate point. This is the heuristic curve. So this is a heuristic curve. This one was a residual magnetic. This is a co-salted force. So this we can when you connect as while here the there will be the leakage and this is a premium. And then we also have to calculate this go to the side. We have to do this wobble. Okay, then we have to do the G107. So this G107, you have to read this wobble. So this is a wobble here. So you have to read the wobble and do the exercise. So I also provide the answer for the exercise. So this is the wobble. Okay, this study this wobble. And for the answer, we got the answer 1 and answer 2. So this is answer for the wobble. So that you have to read the wobble and also then for the answer you can look at the answer book. So this is for your SAR study. Because of the G107 is include the calculation of the maximum demand, also KVS selection. So those things are I provided. So that these things are you have to do this read the workbook and also do this question and answer. So this is that one includes the answer. So this is a workbook 1 and workbook 2 you have to do. So this is the G107 you need to do it. And also you have to do the advanced diploma electrical. To go down here, you have to see the advanced diploma electrical engineering. So electrical diploma 2022. So last week you already finished the G143, 145, 144. So then electrical 2022, you go down here. You have to do the video lesson. YouTube video for electrical engineering lesson and connected lesson. Then you have to see the G143, 144, 145. This way is after you finish G, You have to see the another one. You have to do the G149. So for the G149 is a 3-bit power circuit. So the highlightcombinator.com video lesson. So you read the page 363 to 373, and also you can look at this video lesson, YouTube video, and then you have to do the exercise. So this is the all exercise you have to do for this week.